Welcome everyone to the second class of the Web of Data. I'm slightly wet, as you can see. So today we're going to cover RDF, which is one of the key aspects of this course. It's the foundational data model that we're going to be using in this course. So, in terms of the semantic web, which we spoke about the last time, the semantic web is composed of, we could talk about different components, but here we have three main components: data, logic, and queries. And we'll see a fourth component a little bit later in the course. So today we're going to be focused on data, and data in the semantic web setting refers to RDF, or the Resource Description Framework. So RDF is a web standard, and the first standard was released in 2004, and another newer version was released in 2014. So we're going to be focusing on this aspect of data, where effectively we already have a hint here in this part of the slide in terms of what RDF is. It's a relatively simple data format that's based on triples. So what do I mean by triples? For example, this is a triple here: Ireland, capital, Dublin. So we have a very simple way of making statements. We can also refer to these elements by these three elements here: subject, predicate, object. So Ireland is the subject, capital is predicate, Dublin is object. So this is inspired by natural language processing, and this is somehow seen as the simplest form of statements that one can make. So the idea is that we should be able to, in principle, model the entire world, model whatever data we want with triples. Yeah, so it's somehow the simplest data model that we can use to model the world. We could use a table with two columns, but it's a lot more complicated. So we can also, if we want to integrate new data, which is quite difficult with JSON or with other data formats or XML or whatever, or let's say relational databases, we can in principle just concatenate the data. So we can just take the union of the triples, and now we have a larger data set. So that's kind of cool. So RDF is often drawn as a directed label graph. So here we see a graph, and we have directed edges. So we have some arrows. So there's a difference here between Ireland and country in this relation. So we have Ireland, a country, not that country, Ireland. We have Ireland part of Europe, Ireland capital Dublin, and each of these edges here is, or each of these edges in here is represented by a triple in our data model. Yeah. So conceptually, we can think of RDF in terms of a list of triples like this, or as a directed label graph like this here. Okay. So here is the format where we say that a subject is connected to an object via an edge labeled with the predicate. So a set of triples is this called an RDF graph. So why graphs is the first question. So it's important to maybe motivate why this data format based on graphs was modeled or was chosen as a standard for RDF. So why not tables, for example? Why not say we're going to use relational tables, relational databases, and primary keys and foreign keys and all of this? Or why not XML, or why not JSON, right? So the main reason is that graphs are flexible. So graphs are easy to extend, they're easy to add new information to. We don't have to reflect the schema. So these slides I use in a couple of courses. If you've seen them already, you probably know some of the answers. If you've not seen them, well, that's why they're here. So when we talk about modeling data, in general, structured data, we're going to use relational databases. This is the typical traditional example that we've had for many years. So relational databases are very standard, very well structured. We have here in this case tables relating to a bank, where we have a debit table, a credit table, an account table, a client table, an exchange table. We have foreign keys. We have restrictions. I'm not sure if I have here any. Sorry, we have primary keys. I don't think we have any foreign keys here. So we have this structure called the relational schema, and all our data must abide to it. So you've already seen relational databases before. In the case of situations like banks or libraries, where the schema of the data we want to describe doesn't change very much, this works very well. Yeah, this is really good, relational databases. But in cases where we don't know exactly what we want to model, where we want to collect some data, then it can be more difficult to design a relational schema, because you probably remember having lots of fun in your database course designing entity relation diagrams and or maybe not. I see some places. And relational models for a certain domain. So, however, if we start in, for example, let's say in this case, we're interested in astronomy and we want to model data about planets. Yeah. So we don't really know at the start what we want to model, but we want to have a data set related to planets. So how do we start doing relational data? So we could start by creating at least a table that has the names of the planets. Yeah, we could start simple. So we have a table called planet. We have a primary key for name. And we have the names of the planets. Cool. Okay. So maybe we continue. This is not very interesting yet, but okay, we can add new attributes or new columns to this table. Here we have the distance, which is normalized relative to the distance from the Earth to the Sun. And we can start to add information and add new attributes. For example, we can add a radius now, normalized by the radius of the Earth, and continue with gravity and days and years and temperature and rain. Yeah. Question I often get asked is why are the days negative for Venus? Anybody know the answer? Yeah, it's a retrograde. Yeah, goes the other direction. Okay. So wonderful. Now we'd like to represent some information about the moons or natural satellites of the planets. So the first thing we can think to do, like we've done thus far, is we add a new column here to our table, and we start adding information about the moons. So this symbol here just basically means null in relational databases. Is this a good idea?
No.
No? So what would be better? So why is it a bad idea?
No está normalizado.
So yeah, it's not normalized, right? So we have 0 or many values here. Yeah. So this is not a good relational design. For example, it would be very difficult to find a planet whose moon is Ganymede or Ganymede, I guess. I'm used to teaching these classes in Spanish. Ganymede. So what should we do?
Another table of planet moon pairs.
Yeah, okay. So we're going to create a new table, and we're going to have a new table called moon or natural satellites, whatever we'd like to call it, where we have the primary key is the moon, or it could be the planet. Planet is a candidate key, or no, planet wouldn't be, sorry. There's planets with multiple moons. So we have the name of the moon or the natural satellite as a primary key, and we relate the moons to their planets. And this is a lot neater. We can easily represent the zero or many relation here with this binary table. I say binary because it has 2 columns. Okay, so we continue and we say, okay, we want to model the discoverer and the year. Okay, so now we have a slight complication in that we have, for example, Luna, which refers to our moon. And the question is, what should we put as a discoverer? Or in what year was the moon discovered? Any ideas? So, okay, in this case, it seems like it doesn't really have a clear value, even though in most other cases we can give a clear year and discover. Although even sometimes in astronomy, it's not so clear because they can observe something and not have a clue what it is, and then only later discover that it's of a particular type. So what could we do in this situation for moon to avoid this sort of case? So we don't like nulls so much. Nulls create problems when we go to query data and do joins, and it can have some unintended consequences. So what we could do to avoid nulls in this case would be to break our table down again, and now we have a table for moon discoverer, and we have a table for moon discovery year. So we can mention the year was discovered, the discoverer separately. Yeah, and now we can model 0 to many again if we needed to. In this case, it's more a case of being able to model 0 to 1, optional data. Yeah. And so forth. Now we have a problem that maybe someone might have spotted, but it's quite subtle. Here we put the name of the planet as Terra, and the planet name here is Earth. So I didn't use the same planet name as appears elsewhere in the table. How could we avoid this sort of case? Where somebody wants to reference this table here, but they do it wrong. What's this called? A foreign key. Yeah, so we could define a foreign key and say that this column here should really be a reference to the primary key of planet. Yeah, it should really reference the planets that we already know about. So this is a very useful feature. For example, if we have a company and we have clients, we want to make sure that the people who are buying our products are actually listed in the client table. We're not inventing clients and charging fictitious clients money. So in this case, we add a foreign key to the table planet. And now we have to avoid this situation. We have to resolve or fix this. We can't have something that doesn't appear in the other table. Now, Pluto is dead. Well, Pluto's been demoted to a minor planet in 2006. Decision everybody at university was very happy about, of course. So what does that mean? It means that we have Pluto here in the planet table, and it's not a planet. So what should we do? Yeah, so we could drop Pluto from the table here, and then we would have to be careful here, right? But okay, let's say we wanted to keep the data about Pluto. Is there another option we could go for rather than just delete all the data we've collected?
Move to get another table of microplanets.
Yep. So we could create a new table with a dwarf planet, microplanet, planetoid, whatever we want to call it. And we can put Pluto there. So we're no longer classifying it as a planet. Yeah. So what's the problem now? We have a new problem. Yeah. So we have Pluto here, and Pluto is no longer in this table. Okay. So what will we do with the table? How should we update it?
Making a new one.
A new table? So you mean like a moon of dwarf planet or something like that? Yep, that's one solution. Yep. Another solution might be to just drop the primary key. Yeah.
Because, I mean, we could make another table which lists just terrestrial bodies in general. But planets and dwarf planets belong to the table, and
Yeah.
we have terrestrial bodies first.
Yeah, so we could create some sort of super class of planet and add all of the names of those things to that table. So it would create a little bit of redundancy, but we could also in some databases define it as a view. So it's not really a physical thing. It's just like you say that this refers to this union of tables here. So there are some options. None of them are particularly great. A simple option would be to remove the primary key, which we're going to do here. So the other option, of course, would be to delete the tuple because it's no longer a moon of a planet. Okay, so now we start to think about exoplanets. Yeah, so we start to think about planets around other stars. And in this case, we're like, okay, this is enough. This isn't paying. Yeah. So we give up on the tables. If we look at how to model this as graphs, so if we set aside the relational model and we say we're going to use a graph to represent this data, what we can do simply is just take a node like Earth. We can add another node like Sun. We can connect the two to say there's some relation. We can label the edge to say what the relation is, parent, astronomic body. And we can continue in this way. We can just add more edges, more nodes. We don't have to care about updating our schema or tables or columns or primary keys, foreign keys, and so forth. It's just much more simple, much more flexible. So we keep adding more and more information and our graph grows. Now, Pluto is no longer a planet. What do we do?
Another node?
Yeah, we can add another node, for example, dwarf planet, and then say that Pluto is an instance of this type here. Yeah, it's pretty straightforward. No major changes needed. If we wanted to model exoplanets, well, this isn't really exoplanets, this is different galaxies, but we can model whatever extra information we want. Yeah, so we can say, for example, model information about galaxies and go to a different level or a different area connected to a different domain, and we can continue to evolve rather flexibly. So we can also, as indicated here, we can maybe apply some inference, which is going to be the topic of the next few classes after this week, which will be here we see that the galaxy of the sun is the Milky Way, and its children, we can say then, should be in the same galaxy. The children of a body can't be in a different galaxy to the parent. Yeah. So this is largely flexible, and we can continue in this way. So in terms of the relational data, the pros and cons, and there's one observation I wanted to make here before we continue. which is an important one. So when we're normalizing this data, or when we're trying to adapt to more and more diverse data, a lot of the things we were doing was add a new table. Yeah. And what's happening is we're breaking down our relational database into binary relations. Yeah. These binary relations effectively represent a part of the graph where we can connect, for example, Ganymede and Jupiter with an edge labeled moon. So this is just a syntax for a bunch of moon edges in the graph. Yeah. So what we're doing actually when we're going through this process, when we reached a 0 or 1 or 0 or many relation, was to start to model a graph effectively. So in a graph, what we're doing is we're just starting with this sort of representation here. Okay. So what are the pros and cons of relational data? Some of the pros, or the cons, I guess we're going to start with. The disadvantage or con of relational databases is that we have to impose a structure or a schema from the start. Yeah. So this can be difficult in certain domains where we don't know exactly what kinds of data we're going to want to model. What's the pro? What's the advantage? We have a structure or schema imposed from the start. Yeah. So this gives our data structure. It means that we know more or less what kind of data we're going to have in a relational database. And if you wanted to query SQL, for example, you can just look at the relational schema and have a good idea of what's in there. Yeah. So it's somehow stricter. There are some laws or some commandments you must abide by, which is the relational schema. So it's a bit more inflexible, we could say. So what about graph data, pros and cons? We don't have to impose a structure or schema from the start in the case of graph data, which is a nice pro. Anybody want to guess the con? Yeah, we don't have a structure imposed from the start. Yeah. So I don't want to say that graph data don't have a structure. Of course they do. Often graph data, this would be referred to as semi-structured because we don't necessarily have a schema like in a relational schema sense. So some people define relational schema or relational databases as structured, and all the other formats like JSON and XML and graph data and so forth is semi-structured because it has a structure but no schema necessarily. Yeah. So that's one definition. There are different definitions. We do have structure in graph data, and not just like structure is in this is, you know, we have a graph which is with directed labeled edges and so forth. I mean that over time, if we look at graphs in the real world, which we'll do like Wikidata, they do have an emergent structure that if people follow more or less the same rules, if they don't create duplicate nodes that already exist, but rather connect to that node, if they use the similar labels that have already been used, then you get this sort of emergent structure that is a bit more organic, a bit more flexible, but still, in some sense, there is some structure for that. All the same, without a schema, it can be difficult to know what's in a graph. So if you're given a graph, a huge graph like Wikidata, it can be hard to know what's in there, how to query it, and so forth, which we'll talk a little bit, we'll see a little bit later in the course. Any questions or doubts or comments, disagreements? No? Okay, so we're going to move on to the next part of RDF, which is a key part, which is this idea of naming things. We want to name stuff. And this is a key aspect of the model that's not in other models. So the core concept is that if we want to name things, and you probably had this working with data in projects, you receive some data and it has some mention of Santiago, and you don't know what Santiago it is. You don't know if it's Santiago de Chile, Santiago de Cuba, Santiago de Compostela, or where it refers to. So in general, this idea is that strings are not enough. We need to use some sort of global identification, and we want to tie that down or contextualize somehow what this thing is. So for example, here we have our graph, and we have some mentions of some entities that could be misinterpreted as being other than they are. Yeah. So what do I mean by that? I don't know if you get Milky Ways here, chocolate bar. Maybe, no, some. So there is a chocolate bar called Milky Way. So we could think that maybe this refers to this chocolate bar rather than the actual galaxy. Anybody see any other ambiguous notes? Pluto could be. Pluto. Yeah, so we could misinterpret this. So, okay, another more common case is maybe we understand this is an astronomical graph, right? However, we have another graph maybe somewhere else on the web. Eventually the idea will be to publish these graphs on the web and share the data. We have another graph on the web that's not about astronomy, but it's rather about cartoon characters, for example. Yeah. So here we say that Pluto is an instance of a cartoon dog and Pluto's owner is Mickey Mouse. And that's great. We have these two graphs. And like I said before, if we want to integrate two graphs, what we can do is concatenate the set of triples. Yeah. So we can somehow do that. But if we consider that, then we'll end up thinking that Pluto is orbiting the sun, which might be confusing. Or conversely, we might consider that Pluto, the planet, is owned by Mickey Mouse, which would be unfortunate. So, how do we avoid these sorts of situations? We're going to use web identifiers, and we're going to use something called IRIs and RDF to name things. So, what are IRIs? The idea is that we want to use unambiguous symbols or represent identifiers, sorry, to identify elements that we're speaking about in RDF. So since we're on the web, it makes sense to use web identifiers. So things that start with HTTP that we can look up, that are clickable. We can click on the thing and see where it goes, see what data are provided. So there are kind of three concepts, and most people will not have heard of IRIs before. Even if you're a web developer, you've probably never heard of IRIs, but URLs everybody should know. Yeah. So a URL is a uniform resource locator or location. The location of a resource on a web. A resource here is thinking about a document, a web page, a PDF file, an image, things like that. So they refer explicitly to documents on the web. We next have the concept of URIs, which are uniform resource identifiers. And this was used in the original version of RDF for identification. The core idea here is it looks exactly the same, but it doesn't need to be necessarily a location of something. It doesn't need to be the address of a document. It can just be an identifier. It can identify in this way things that can't be located on the web. So things that can't be located on the web, I can't be physically located on the web. A city cannot be physically located on the web. So this is the concept of URI. It's not necessarily a location. Yeah. So that allows it to identify things that are not inherent or located on the web. So it can just be a name for something. Of course, when we look this up, in some way, we'd like to get back some data about the thing. So it's not going to give us a 404, but it's going to say, okay, I can't return you the city, but if you look here, you can find some data about this city or this person or this book or whatever it is. And we have the final, finally we're arriving to IRI, which is another generalization, which is an internationalized resource identifier. So at some stage, people realize that it's kind of stupid that URLs and URIs should contain ASCII characters, because there's lots of languages that don't use ASCII. Yeah. And what you would have seen at some point is this sort of ugly percent encoding that now browsers will try to hide from you if you have an I with a tilde or an accent. Yeah. And the situation, of course, looks even worse. Let's say if you're looking at Chinese alphabet or different languages. So IRIs, they allow you to use Unicode, a large part of Unicode as part of the identifiers. Yeah, so Unicode is growing all the time. Okay, so we're going to use web identifiers, and in RDF 101, we're going to use IRIs to identify things. Okay. So we'll use IRIs with prefixes because they're kind of long otherwise. So often you'll see this sort of syntax where rather than writing the HTTP colon, blah, 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 we're going to abbreviate this and we're going to have to define this prefix somewhere. So this example, when I use this in the classes, it doesn't refer to anything in particular. It's just used as an example. Later, we'll talk about real prefixes and we'll talk about what vocabularies exist. There are things on the web that allow us to describe different types of entities. But for EX, it just means example, and it just refers to some arbitrary prefix that we're going to use. So in this case, this denotes a prefix name for this URL here, and Dublin is a local name. So this is equivalent to saying this. It's just a shortcut. It's nice and more concise and more readable. So some frequently used prefixes that are used for describing RDF data. RDF has not only a data model, but what's called a vocabulary, a set of very minimal terms that everybody will use. And we'll see some of those quite soon. We have XSD, which we'll use for data types, which we're going to also talk about a little bit later. RDFS and OWL will be the subject of the next kind of block of classes. Yeah? So we're going to talk about ontologies and RDF schema.
Perfect.
Yep.
Every identifier or resource should be like in the HTTP protocol.
Yeah, so it's a very good question. It's not necessary. So we can have, for example, in some case, we might give someone's email, and then we can use the mail-to protocol. We could have a file that's on FTP, which is not so common anymore, but we can use that as well. So it's not necessary, but in general, it's recommended, and we'll get to that a little bit later in the course. It's kind of later about putting this on the web. But the core idea is that when we use identifiers, we want them not just to be names, but when we click in it, it will bring us in the web to what this thing is. It will bring us to a description of what this thing is. So if we see Santiago in our RDF data, it's a link. We can click on that, or we can dereference it, like use it a software agent to go and fetch and ask what this thing is. Yeah. So it's highly recommended to have a HTTPS protocol.
So, but it's not part of the standard.
No. It's part of more guidelines that come later. Yeah.
Thank you.
More questions? So other kinds of common protocols, sometimes people use URNs, your universal resource names, that they're not really supposed to be links. They're DOI, bunch of others. Yeah. Okay. So from strings, we spoke about it in this generic way. We have all these strings, but we know that these strings can be ambiguous. For example, Dublin could be a city in Ireland, or it could be an Irish bar in Bella Vista. What we're going to do is use these web identifiers. We're going to have to create some sort of namespace or some URL graphics, and we're going to start naming things. So we have Ireland here, part of Europe, Ireland type country, Ireland capital Dublin, Dublin population 1 million. Two things of note. This is the first RDF vocabulary term we're going to see. The RDF people, they just wanted to define the RDF data model. They didn't want to define a vocabulary for how to talk about everything. But they thought that this is so common, having to say, for example, that a country is a country, or a person is a person, Aiden is a person, web of data is a course, that they decided that it would be not so great if everybody defined their own term for this. So they said, okay, we're going to standardize a few terms that everyone can use. So type is basically saying this is an instance of a class. That's a slight simplification we'll get to later, but that's the idea. Okay, so now our RDF graph looks the same, but all the terms are somehow these identifiers. The second observation is that we've not changed 1 million. Yeah, so we'll come back to that, but it doesn't really make sense to. Yeah, we're going to define a special syntax for these sorts of values. So the special syntax we're going to define for numbers and booleans and dates and so forth are called literals. So we have IRIs so far, which are these web identifiers for things we want to describe. And then we have literals, which is this question of what to do with the numbers. So the question is, would it make sense to assign IRIs to numbers and booleans and so forth? Sometimes, but not in the general case. So if you have visited Wikipedia, you might have found sometimes that they have articles about numbers. You can go and it will tell you if a number is prime, what kind of significance it has, and for that purpose, perfect. It's great to assign an IRI for that. But just to give a numeric value, it doesn't really make much sense because it's not ambiguous. It's a numeric value, it's somehow standard, and machines can use it to order, to apply operations like subtract, or extract the day from the date, these sorts of operations. So RDF allows literals in object positions. So literals are for data type values like strings or numbers or booleans or dates or times, these sorts of things that machines or software can parse and manipulate and order and do various operations with. This is a big debate. They're only allowed in object position. Later, there was a lot of people who argue that no, they should be allowed in the subject as well. Why are they relegated to only being objects? So the idea is that they're kind of the value of properties. They're not really the thing you talk about so much, but there's actually some debate about that. But in the RDF 1.1 version, they're only allowed in the object position. So here we have our table again. We could say that this case is okay. This case is not okay, and this case is not okay because we can't have literals in the subject or predicate position. So data type literals, and there is an exceptionally complex list of questions here or things to define. So RDF uses an existing standard called XSD, which is XML schema. What's the D? Data type, I guess. So there's a lot of questions. If you want to model this sort of thing for the whole world, there's a lot of questions you need to think about. So it's okay, maybe straightforward, but dates, for example. How do we model dates? How do we model dates for the whole world? What's the minimum year? Should we start at minus 10,000? Should we start at minus 1 million? How far into the future should we model this? Yeah. Can you compare two dates? So if you have 2014, 12, 13, is that less than 2014, 12, 14? Is the 14th, does the 14th of December come after the 13th of December? Depends on the time zone. What if the time zones were plus 12 and minus 13? So there's lots of subtleties or things that need to be thought about. So there has been working groups working on this sort of stuff. The nice thing is that they define, of course, the date in the logical format of year, 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 month, month, day, day, and not some day, day, month, month, year, 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 year is okay, but month, month, day, day, year, 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 is it a travesty? I'm sure. Who thought that was a good idea? So what's the benefit of this? You can order by string and you'll actually generally get a pretty good ordering of temporal ordering as well. So here we have ints, we have dates, we have booleans, we have strings, and if the data type is omitted, it's a string. So this is a string. So by default, we essentially assume things without data types to be a string. And in this case, it's important to note, this will be important for the lab as well, that if you write 200 in quotes without a data type, it's considered to be the string, the character 2 followed by 0, followed by 0. It's not considered to be a number, a numeric value. Yeah. Okay, so as mentioned, many of the data types are borrowed from XML schema, which is this XSD prefix we saw. I'm not going to go into all of the details. Well, I kind of am, but I'm just going to, I'm going to jump over them as quickly as possible. So here we have different things relating to dates, times, binary data, booleans, and then we have all this numeric stuff here, decimals, integers, and we have some floats and doubles and so forth. So I'll go through a little bit of detail because we need it for the lab, but I'm just going to go over it very high level. We have booleans, and that's called XSD boolean, true, false. We can use 1 for true, 0, and this is case sensitive. We have numeric data types, and we have here, this sort of hierarchy here means derived from. So it means that somehow this is a specialization of the higher level type. The highest level numeric data type, at least at this level, is decimal. So this is basically anything we can describe in a decimal format. We have integer long, int. Int is the sort of classic computer programming int. So that for that reason, it's different from integer. It's 2 to the 32 or minus 2 to the 31 and 2 to the 31 for signed int. We have shorts and bytes, non-negative integer, positive integer, unsigned long, and so forth. One question might be, why is it useful to have all of these? It's useful later if we want to define, for example, that an age can be a non-negative integer. It can be useful to say, okay, this is the sorts of values this can take, and that helps us restrict the values that certain properties can take, for example. Okay, here we have two types that are not derived, that are double and float. Any ideas why they're not? This is a very common confusion as well in semantic web area. People who are programming stuff don't really, they wonder why double is not compatible with decimal or why it's not derived from decimal. So we have double and float.
Is it because it allows things that are not numbers?
So yep, it has some syntax like not a number, infinite, and so forth. Yep. And there's a second reason. And the second reason is that these are considered to be approximate numbers, and there's no notion of approximation here in decimal. So this can give rise to some weird things, like you have a double in one data set and you have an integer in the other data set, and you can't compare them, even though intuitively you can say, well, these should be comparable. They're both the numbers, but the double or the float is based on this IEEE floating point format. Yeah. So they're not strictly comparable, even though most systems will still compare them for you. Okay, so we have temporal data types, we have time, we have date, date time, and date time stamp. The nice thing about date time stamp is, okay, we have a date, we have a time, but the time zone is obligatory. So we have a total order. We don't have this question of is this day less than this day. We have things for durations, how long something lasted. Yeah, we have something for date-time duration, if we just want to measure duration in day and time. Or we have year-month duration, which might be more useful, for example, for something that's very long, maybe a war or something like that. Or maybe something even longer of centuries long, for example. We can specify a day, a G day, and G stands for Gregorian. So this means a day that happens every month. So we can specify the 14th, and that refers to the 14th of whatever month. We have G month, where we can refer, for example, to December as a recurring month. We have G month day, which would be useful, for example, for a birthday. This person's birthday is on this date in this month. We have a year, and this one is possibly important in the sense that it's a common mistake as well in the labs that people model years as integers, which kind of makes sense, but we actually have a more specific data type, which is the G year, Gregorian year, which tells us that this really specifies a year in the Gregorian calendar. And then we have G year month. Yeah. So a specific month within a specific year. So we have data types for this. We have some strings, string data types that are not so much used. Of course, the string, high-level string is used a lot. There's a bunch of garbage here that should never have been included in the specification. There's some stuff where this is related to internal XML syntax. It's really meta. It's just not good to have here, but okay, we can just ignore it. Base 64 binary and hex binary. We can specify some binary data, maybe some hashed data or whatever it is. We can specify IRIs or URIs. We can specify HTML syntax, and we can specify this XML syntax as well. So we can give a value that's actually an XML document, for example. Okay, so another type of literal that is distinct from the data type literals that we saw is the idea of language type literals. So this data model tries to be a model that is useful for the web, and that involves different languages, of course. So what we can use is a language tag to specify that this literal is in this language. Yeah, and we use the standard 2-letter codes for this. We can also use hierarchical types. It might be difficult to see what that says, so I'll just write it here. And the language type we use an @ symbol, and then we can put en, or we can just do so the tag at the end specifies the code of the language that we're using. So we have string, and then we have @ and some language tag. And there's no data type associated with this. There's a special kind of reserved data type you don't express for this, called plain literal or language string. Okay, so that's language tag. Just to mention as well that if you want to, you may have seen these sorts of codes. You can use these as well. So you can do, for example, Chilean Spanish. You can use these sorts of tags as well if you'd like. Okay, any questions or? So again, maybe just to mention briefly that, this seems kind of maybe relatively trivial, but there's a lot of discussion if you want to do this in a global way, in a way that's standard, that have to be resolved so that this sort of works for the web at a larger scale. So next we have the third type of RDF term, which is the most mysterious, and it's the one that some people, nobody loves it. Lots of people hate it for sure. It's called blank notes, and there's a lot of debate and discussion about this all the time on the sort of mailing list and communities. So the idea of blank notes is that having to name everything is hard work. So if we have to name every single thing in our data set and provide a link that brings us to some location on the web that describes that thing, it can be quite tedious. It can be a lot of work. So for this reason, RDF gives us a third and final type of term that we can use in our graph called blank notes. And essentially the syntax is like this, where we have an underscore, which represents a sort of blank prefix, and then a label for the blank. It represents the existence of something. So if you did first order logic some time ago, you might have heard of existential variables, the backwards E. So this is sort of somehow the semantics of these blank notes. Yeah? So they represent that something exists. And they're often used to avoid giving an IRI or a web identifier to something because it's just not really important, or we don't want to do that. It can only appear in the subject or object position. So we can have this is okay, this is okay, this is not. We can't have them in the predicate position. So correct, and incorrect. So we're going to come back to that later. It's going to leave it a little bit mysterious for a moment. It's going to be a little bit kind of hard to motivate it yet, but we'll get there. We'll have some examples where like notes are useful. First, as a summary of the RDF terms, we have the three IRIs, literals, and blank notes. So as it says, blank notes are still a little mysterious right now. We'll cover that. Here is a summary of where we can have the different types of terms. So subject can be an IRI or blank note. Predicates have to be an IRI, and objects can be any of the three terms: IRIs, blank notes, or literals. Okay. So modeling data in RDF. Let's try to model something in RDF. So we have my favorite movie, Sharknado, here. And it states that the text states Sharknado is the first movie of the Sharknado series. It first aired on July 11th, 2013. The movie stars Tara Reid and Ian Ziering. The movie was followed by another one called Sharknado 2, the second one. Yeah. So what we'll be looking at in the lab will be on Wednesday will be this. You'll be given some text with some facts, some information about some entities, and you'll be asked to model this as an RDF graph. So we can maybe start a little bit just to mark down some stuff. We can do the start of it. And we're going to draw it as a graph. You can in the lab, you're going to write it in a turtle syntax that will be converted to a graph. So you can view it as either a syntax or as a graph. So we'll do it as a graph here. So Sharknado, first thing we're going to do is just put down the things that we want to describe, right? So Sharknado, not so difficult, is the first movie of the Sharknado series. So the first thing we notice here is we have two things called Sharknado, but they're not the same, right? So what we would probably want is we want to have another thing called Sharknado. I'm just gonna series. Okay, and we can say Sharknado is the first movie of the Sharknado series. Okay, so we can maybe say that this is a property of the Sharknado series. It doesn't, matter so much in the lab. It won't matter either too much. First movie. If you wanted, you could do it the other way and say first movie off. So typically, just to mention about the direction, in real world modeling, people try to model in the direction of the cardinality. So for example, if you go to the page of a country, you don't get a list of all its citizens. But if you go to a page about a person, you get their citizenship, as a rule of thumb. Sometimes that doesn't work, and you can have as well, you can have inverse relations. We can model that stuff perfectly fine. Yeah. Okay, so what else? We can have second movie. I'm just going to abbreviate. I'm going to start to abbreviate some things. Example, Sharknado 2. Okay, so we have the first aired on July 11th, 2013. So this is, of course, relevant to this movie here. Yep. So we're going to do X first aired. So what should we put here? Should we put, for example, July 11. I should know the date by heart, of course, but 2013. No. So this is kind of we could maybe, but it would make a lot more sense in this sort of case too. Usually we draw literals with boxes, so we write them like this. Then we should use the proper syntax so things can parse it later. Yeah, so we don't have to guess what this format is. So we're going to put it as July 11, and we're going to type it as XSD date. I'm just going to abbreviate it slightly. Yeah, so now we have a standard syntax, so we can parse and we can read and we can order and we can, no matter where we find this data on the web. The movie stars Tara Reid and Ian Ziering. Okay. First. Read. Ian Ziering. And what else are we missing?
Sequel?
Okay, so we could add, now one could argue that this is not necessary because it's implied by the first movie, second movie. But we can also say, I mean, it's followed by. We could also say it's useful to have that. It'll make things easier to query. Yeah, so there's an argument to be made to omit that, but we can definitely add that. I think it's useful. Anything? Sharknado is the first movie of the Sharknado series. It first aired on this. The movie stars these people. The movie was followed by another called Sharknado, the second one. So there's one thing that's key, and there's another couple of details we could add.
We can specify that Sharknado and Sharknado 2 are instances of movie.
Yeah, exactly. That's one thing. So we can say here it somehow states movie, right? So no, this is between the series and the sorry. We're going to create an example movie class, and we're going to use RDF type here for this. And here we're going to do this, and we're going to create RDF type. So we say that they are the same class, which is movie. Here, I mean, we could probably infer that Tara Reid and Ian Ziering are people, but we don't actually say that. We don't mention people here either, so we don't have to do that. Anything else we could add here again? Same thing. One could argue that maybe the text isn't explicit about this, so that's okay, but you could add it if you want. Movie series. But there's one crucial piece of information that we still haven't modeled, and maybe it's not clear from the way I'm abbreviating. But essentially, an IRI does not replace a name. So we've never said what these things are called. Yeah, we can kind of infer them from the IRI, but just to give one example here, what we should write is, and there's a special property from this RDFS label, we should write the name of the thing. And in this case, we can give it a language tag and say that that's the name in English. Yeah, we could do that as well for Sharknado, for Tara Reid, and for Ian Ziering. So this more or less is what we could consider. Here we have the answer, maybe for the people on Zoom who are wondering what we were doing. It's a little bit difficult to, well, maybe I could have, but okay. But here's somehow the model in RDF of what we were trying to do. So key things here, we have the names of things in as literals, as language type literals. We have dates, and we've indicated the types of the entities as well. So this will be very similar to what you'll do in the lab. We'll have a couple more details that we need to look into. So this would be maybe a more straightforward example. So in terms of modeling, what we use for modeling data or for representing some claims or statements, we have properties, which are essentially the terms that we use as predicates. So the predicate is like the second column, the position in a triple, and properties are the terms that we put into the predicate position often. They can also go in other positions. So RDF terms use this predicate. So we have, for example, type, we have a relation first movie, we have a relation stars. These are properties that we can describe of nodes. We also have conceptually this notion of classes. So these are used to group resources that are similar. So movie, an actor, a building, a course, a university, a person. These are all relevant classes. And we can use the property RDF type to instantiate a resource, to say that this resource is an instance of this thing here. Yeah, so this is Sharknado type movie. So just to mention, we're going to talk a lot more about that in the next class. So we're going to talk about the somehow semantics, or what these things mean and what we can define about them. So modeling in RDF is not always so simple. Yeah, so we have another example here, which looks pretty straightforward. It states model the following in RDF. Batman Returns stars Michael Keaton in the role of Batman. So that seems pretty straightforward in the sense that we've already done something very similar here, no? Rather than Sharknado, we'll have Batman Returns, and then rather than Tara Reid, we'll have Michael Keaton. But we have the problem of the character, right? So now we're saying that they play a particular character. So we could say, we could try something like this. Batman Returns has the character Batman, and Batman was played by Michael Keaton. Yeah. Okay, this is maybe not bad, but let's make it a little bit more complicated. So now we have Batman Begins, stars Christian Bale in the role of Batman. We find this, maybe this is on another document or somewhere else on the web we find this. So we end up, if we model the two using the same pattern, we have Batman Returns as character Batman and Batman Begins as character Batman, Batman played by Michael Keaton and Batman played by Christian Bale. And the problem now is we don't know which actor played Batman in which movie, right? So it's not so straightforward. We can't really break this down into a simple binary relation between two things. There's really three things, no? The movie, the actor, and the character. And we need somehow a tuple. We need an Henry relation for that. We can't easily break it down like this. So one might argue that, okay, what you could try to do as well is you can mention that the movie stars this person. Yeah, and you could say, okay, the movie stars this person played this character. Then we could pretty much infer that the person played that character in that movie. Yeah, but that's not very satisfying, no?
No.
Because we could have a case, okay, this is a fictitious case, where we have characters playing multiple roles in the same movie. In this case, it doesn't work, but there's Dr. Strangelove, there's lots of examples where actors play the same character, various characters in the same movie. And in this case, yeah, we have a mess. It's like, okay, who plays which character in which movie? It's completely unclear. Yeah. So how we model this sort of data, and here we don't know who played which character in which movie. So a better way to model this sort of data would be to use an Henry predicate. And yeah, this wasn't real. They didn't really play the role of Robin in these movies, but okay. So how we would do this in a more general way, in a more principled way, would be to use an Henry relation. And the idea is essentially to introduce a node to represent the relation. Yeah. So we add a new node, and this node somehow represents the participation, a more abstract idea of a participation in a movie, like a credit or a role in a movie. Yeah. We use a blank node in this case with the underscore, which means that, okay, we don't bother to name it. If we wanted to, we could say the character Batman in the movie Batman Returns as played by Michael Keaton, but it's very long and long-winded, yeah. So here we have blank nodes for this, and we have each blank node is connected to three elements: the movie, the actor, and the character that was played. Yeah. So this is a better way to model Henry relations. Using this trick, although graphs are more natural for binary relations, we can also use graphs to represent Henry relations. So we can pretty much model a full relational database using this trick. There's no, we can model essentially arbitrary data in this way. So the core idea again is to represent the relation as a node, yeah, as a thing. And then we describe that thing, and then things are straightforward. Okay, so we have a similar example to what we saw here, and one thing that's not really nice in this example is we have first movie and second movie. Where's second movie? Second movie, because we're encoding numbers there somehow, the first and the second, which would be nice to actually represent in a slightly different way. So model the following in RDF. The first movie in the Sharknado series is Sharknado, the second movie is Sharknado 2, the second one, the third movie is Sharknado 3, oh hell no. So we could model it just as this, similar to what we were doing before, Sharknado series, first movie, second movie, third movie. It's not very general, yeah? So what we're missing here is a way to represent order in graphs. Graphs don't have order inherently, but lots of people need order for representing data. Super useful to say this is the first element of something, this is the second element. So RDF introduces, and this is quite a hotly debated feature as well that some people don't like, some people like, some people don't like, a vocabulary for representing ordered lists using a graph. And what they do essentially is I'm more careful this time. Hasn't exploded yet. So what we do in RDF is we define essentially a linked list that defines a kind of an ordered list of elements. So we have three terms for this that are defined in the RDF vocabulary as part of the standard. We have rest, first, and nil. So essentially rest is used to continue a list. First is to give the element of the list, and nil is used to end the list. So if we wanted to define the Sharknado series, the first movie is Sharknado. So we have this property movies that points to some blank node, and the blank node says first Sharknado, and then it says continue the list here, P2, first Sharknado 2, continue the list here, Sharknado 3, and then it ends the list with nil. Yeah, so this way we can represent an ordered list as a graph. So this is called an RDF collection. So not just for the Sharknado series, the nice thing about this is we can use it anytime we need order to represent order in our data using RDF. Yeah, so we can use these collections. So as everybody knows, lemonade, if you want to make lemonade properly, you have to add sugar first and then water and then lemon. Everybody knows that, of course. I didn't just invent that. So okay, here we have a list for that. So here we use blank nodes. This is a common use for blank nodes, is to glue things together. Yeah, it's really, there are nodes that help us to define Henry relations, or they help us to define parts of a list that are more abstract or that don't really need a name. We don't need to offer a link to find out what this thing is. It's just a structural element. So which modeling is better? So in this case for lemonade, we have sugar, water, lemon, using a collection, and we have this modeling here which just directly says lemonade has 3 ingredients, and this is a common issue as well in the lab. Which modeling is better? So it depends on whether or not the order matters. If the order doesn't matter, if there's no order between these ingredients, they're just ingredients, this is much simpler, much better. Yeah, it's much more concise. Things will be a lot easier to query and so forth, so we can do that. So if there's no order between these things, or there isn't an order that's defined elsewhere. For example, if we're defining somebody's children, we don't necessarily need to put them in an order. Yeah, we could say that there is an order from youngest to oldest or oldest to youngest, but it would be better to use this sort of modeling here to say child, 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 and later we can define the dates of birth of those children. Yeah, so there's an order induced in that way. So in general, unless there's a very strong, compelling reason, we should prefer this modeling here. Yeah. Oh, it's gonna come back. Okay, cool. So this is by default what we should prefer. But if we want to capture order, we can use the first. We can use these RDF collections for that. So in this case, if we really wanted to, for some reason, say that sugar should be added before water and then lemon, we could do that. Okay. Yep.
Does it like add more complexity for the querying later?
Yeah, it does. So we have some tricks to query, like to get given lemonade, we have some patterns so we can use to get out all of the elements of the list in Sparkle in the query language. But the problem is that this can be of arbitrary length. So this can continue this list for 25 elements or 50 elements. So it's not going to be a fixed size pattern. We need some sort of recursion to query that. So there are some things we can do, and Sparkle provides some ways to extract elements or to extract all of the elements of a list, but it will be more complicated. Yeah.
And what if like one instance is in the first syntax and the rest of the instances are in the second part?
Yeah. So usually, as noted here, there's a subtle difference in that here we use the property ingredients. So we'll use that property when it should take a list, and here we just say ingredient singular. So we should use different properties for that sort of case. Yeah, but we might, if we think that both of those cases might be used, ingredients and ingredient, we'd have to do like a union or reasoning or something too. Yeah.
So it's like a problem for now because we are not like using a standard for naming things.
Yeah, it would be, I would say it's a problem. It will become a problem if we don't have a way of mapping or integrating between these two ways of modeling the data. Yeah. I would say at the same time, this is relatively rare where you have like these two main, well, no, it's not so rare, but the two ways which we'll discuss later, there's two ways. If we have two ways of modeling equivalent information, one is to expand our query, which is to make our query more complex to capture all of the cases, or the other is to use reasoning, which we'll talk about later, which will use ontologies to be able to figure out these two things are equivalent. So if somebody asks for it in this form, I should also give it represented in this form. Yeah. Okay, and so if the order in ingredients matters, the collection above is necessary. But if we can avoid this sort of thing at all, it's better to go with this option here. Why is that? So we mentioned that it's more difficult to query, but aside from that, blank nodes add complexity. They add complexity to processing RDF graphs. And for this reason, they're maybe not super popular. So the general idea is that blank nodes are local identifiers. So it's sort of like if you have an SQL query, or maybe you have even just a program in Python, you create names for variables, and those names don't really matter. Yeah. You could change that instance or what the name of a variable everywhere, and it doesn't change the semantics or what the program actually does. Yeah. So this is a similar concept for blank nodes, that these names that we put here, B1, B2, B1, B2, they're local. They're kind of local to that, locally scoped. Yeah, they don't have meaning outside of the particular RDF graph. So if we have these two RDF graphs here, essentially, if we combine these two RDF graphs in the standard way, which is to concatenate triples, we're going to end up in a slightly strange scenario where our RDF graph will look like this, where we're going to combine B1 and B1, and we're going to combine B2 and B2, and we're going to end up with, for example, this ingredient that contains pecan and contains citrus, which was never really the intention. These are supposed to be distinct local labels. So for this reason, we don't do this in RDF. It defines a special way to combine RDF graphs with blank nodes, which is basically intuitive enough. We're going to create distinct blank nodes. We're going to distinguish the blank nodes in the two graphs in some way. It doesn't matter because the names are arbitrary. In some way before we take the union. So in this case, we're going to create, for example, B1, G1, B2, G2, B1, G1 or G2, B2, G2. Yeah, so we create somehow distinct blank nodes for each graph. And then when we do the union, everything is okay. We don't have this, what's called a blank node clash. We don't falsely combine two blank nodes that happen to have the same label. So blank node names aren't important, as we saw in the last thing. So we could look at these two graphs and we could say, how are they different? They're different in the sense that the labels of the blank nodes are different. Does that matter? Does it change what we're describing? Does it change what we're saying with these graphs? No, it doesn't. So this is a notion called isomorphism of RDF graphs. So essentially it means that there's a one-to-one mapping of the blank nodes, such that if we apply the one-to-one mapping, let's say from this graph here, we get exactly the same graph here. Yeah. So you've seen graph isomorphism, I guess, before in some course, or homomorphism. Okay, so this is isomorphism. So we can see here intuitively that these graphs are the same. Okay, it's not too hard. In this case, they are not isomorphic because we've changed the order of the elements here. Yeah, so these two graphs are now different. We have the things in a different order, not just the blank node labels are different. So how about this case? Do we think that these two RDF graphs are the same, by which I mean formally isomorphic? Let's have a look. So we have citrus. Okay, and there's something that contains citrus, and here we have something that contains citrus, and that something also is the ingredient of lemon cheesecake, so that fits here. And we have this thing here, which is an ingredient, an ingredient of lemon cheesecake, which is the case here. And this thing contains gluten, which it does here. So we can say that, okay, we can look at it for a little bit and we can figure out eventually that this is isomorphic. Yeah. So these two RDF graphs are the same. It's just that we have a one-to-one relabeling of the blank nodes. So these variables. What about this case? So here I haven't given any edge labels just to keep things a little bit neater, but we can say that every edge label here, just to make the hardest case possible, given that it's a Monday morning, we like to be stimulated on Monday mornings, is every edge label here is the same. So they all have the same predicate. Yeah. So are these the same? Are these isomorphic, these graphs? Any idea how to program, even maybe, how would you program an isomorphism test? You had to implement an algorithm, a program to take two RDF graphs and say if they're the same or not.
I think that we need to list up all the nodes. How many relations do they have coming in, coming out? And then verifying that the sum of these things match when they need together.
Yep. So you can extract some, these are called invariants from the graph. So you can say, for example, that if this node here has two edges going out and one edge going in, it can only match a node that has two edges going out and one edge going in. Here. So that will, I think in this case, give us a partition of two. I think all the nodes will have two cases. One will be two in, one out, one in, two out. I'm not 100% sure of that, but I think that's the case here. So that would help. If this were the undirected graph, it wouldn't help at all because it would be a completely irregular graph and invariants don't help us. So there's a certain regularity, but yeah, that would be common. So we could start with that idea. This is maybe getting a bit off topic. I didn't want to get into this, but if we want to continue that idea, so we can say, okay, this has one edge coming in and two edges going out. So we can maybe assign this a hash based on that information, a number or a color or something. And then we could say, we'll call these nodes blue. The ones that have one in and two out, we're going to call them blue. These nodes. So this one here would be blue as well. This one has two in and one out, so we'll call it red. Yeah. Red, 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 blue, 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 blue. I guess I didn't check it very carefully, but we'll assume so. So what we can do then is start to pass the colors here. So we can say this is a blue node that has not just, we not only count how many edges it goes out to, but what colors they have. So we can say, okay, this node has a red outlink. It links to a red node and it receives a link from a red node and a blue node. Therefore, it's this color. And we can propagate somehow the information through the graph. That's still not enough, unfortunately, but it helps in a lot of cases. So are the two RDF graphs the same? Yes. Yes. So the idea here is to give an idea of why this is hard. So we have one isomorphism here. There's probably more. So if we look at it, we can see here, for example, that the purple receives, just to take one example, the purple receives a link from yellow. So here we see purple receives a link from yellow. And it gives a link to cyan and to orange. So it gives a link to cyan and to orange. And if we look at all of the nodes, we'll see that they preserve the edges of the other graph. Yeah. So they are the same graph, isomorphic graphs, just drawn in a different way. So this is a hard problem to solve. This is something called GI complete, where people kind of cheated. So often you have to prove if something is NP complete or P complete or whatever. So instead of doing that, in this case, the people said, for graph isomorphism, we're just going to create a new class, graph isomorphism. Yeah. So, and we're going to say that graph isomorphism is graph isomorphism complete. Yeah. So this is somehow a class that's between P and NP. It's an intermediate class that people don't know if it's NP, hard or not. So it's a hard problem. It's not as hard as NP, but or it might not be as hard as NP. But this is caused by blank nodes. So if we want to say if two RDF graphs are the same or not, now we have this GI complete problem that we have to solve every time. Of course, that's in the worst case, right? These sorts of cases are not very common in RDF data. Often we'll have very specific information that we're describing. Okay. So any questions here, that's? So just for reference, I'm going to try to go quickly-ish through this. It's just some syntaxes we can use for actually writing RDF down and publishing it on the web. We have n triples, which is a line delimited format, and all of the formats we're going to see describe the same graph, which I've put here with prefixes. N triples is a line delimited format, the most simple format or syntax for RDF. There's no prefixes, no abbreviations, nothing. You just put the full IRIs on a line, and you put 3 RDF terms on a line, put a dot at the end, and then new line. Yeah, so that's RDF triples. RDF XML, which I'm not going to discuss in detail because it's horrible. It was also one of the biggest mistakes of the community was that this was the only standard format that was available, and everybody looked at it and was like, what the hell is that? It's XML but weird. The idea was, okay, briefly, that there was a lot of interest in XML, and XML was seen as the structured or semi-structured format for the web around that time. And people thought, oh, we have this new RDF thing, why don't we just use XML for syntax, and that way we can use all these XML processing tools to work with RDF. But there's many reasons why that was a bad idea. In hindsight, at the time, it's very understandable why they wanted to do that. We have RDFA. I don't know what the A stands for. Annotation, maybe. So we have ways to embed RDF into HTML. So essentially the idea is that if we're describing maybe some recipe and we have the list of ingredients in our HTML, we can embed some RDFA to give the structured version of that, to say that this ingredient of this recipe is such and such. So here, for example, we say that this relation here that we're describing with this list is ingredient, and then we provide the objects of the triples, which would be the different ingredients, which should be related to the higher level element. It's not super intuitive, written in this way to model RDFA. JSON-LD is growing in popularity. So it's essentially JSON, but you add a little bit of metadata called the context, which allows you to somehow use web identifiers within the context of JSON. So we add some extra information about what kinds of vocabularies we want to use, what are the namespaces we're going to use, what are the base URLs we want to use, and then we have something very JSON-like later that essentially will generate some IRIs or web identifiers for us within our JSON data. This is becoming increasingly popular, JSON-LD. The syntax we're going to use in the course principally is Turtle. And it has a major benefit that it will be quite similar as well to Sparkle, which will be the query language we use later based on the same syntax. So it has a lot of tricks for abbreviations. So we have a base declaration here, which allows us to give relative URIs or IRIs. So essentially in this case here, we can just write with angles some local name, and that will be stuck onto the base URL here. We also have prefixes, so we can just define our prefixes, RDFS or example1 or whatever prefixes we'd like, and then we can use these abbreviated forms here to refer to the full URI form. We have as well some syntax for abbreviation to repeat elements of the last triple. So we have Jen, a person here, and if we put comma, then we say to repeat the subject and the predicate. So Jen, a person, Jen, a student, Jen, a female, Jen, whatever we'd like to do. So we can just put comma. So this says repeat the last subject and predicate, Jen, and then we have female here. Then we have a semicolon, comma. This means to repeat only the subject. So this means just repeat Jen, not the property. Then we say Jen, RDFS label Jen. And this says repeat the subject, Jen, allergy, citrus, colon, Jen, location, and then we have some other stuff here. And this stuff we'll talk about in a second. So we have an abbreviation for RDF type. Now we can just write This is my favorite abbreviation of all. This is nice. We have some data type shortcuts where if we write the thing without quotes, similar to JSON and other syntaxes, it interprets it as a number, it interprets it as a decimal or as an integer if it's a whole number. And we have blank note shortcuts. So what we're doing here is we're saying Jen, location, and then we have a blank note, and that blank note has latitude 53.3 and has longitude -9. So we have a pretty nice way to represent this. We also have a way to represent shortcuts for collections, where we can, if we wanted to in Turtle, we could write out this collection in this way, which is super tedious. So we can write it out triple by triple for every edge here. We could write it out with the blank note abbreviation in the same way here. So we have lemonade, where we have our base I right here, lemonade ingredients, and then we have this nested blank note structure, which is still pretty ugly. So we have a third option, which is very convenient. which is just laminate ingredients, and we use parentheses and say what the things are. And that takes care of having to define this thing manually. This is only possible with blank notes, this sort of syntax, because we've not explicitly named these elements here. Yeah. So it's only possible with blank notes because we need some glue nodes to make this sort of syntax work. We need some internal structural nodes, and only because their names don't matter, we don't have to give their names here, so we can just put it in parentheses and we're done. So turtle is the syntax we're going to use for most of the course. So we're going to play with it. We're going to practice with that on Wednesday as well. Yeah, so any questions? Okay, so that's RDF. This is the data part of this overall picture. RDF is broadly adopted. So I know this is a postgrad course and we're talking about researchy stuff. But what most people probably don't realize is that a large portion of websites already have RDF. So you think of a website, it almost certainly has RDF in it. So this is a list by W3 Techs. This is a list of different data formats that are used within different websites embedded into web pages. So we get the percentage of websites that are using these different structured formats. At the top, we have Open Graph. Has anybody heard of Open Graph? Facebook, right? So this is a format that Facebook defines. Twitter cards, people who've done some web development may have heard of Twitter cards. If not, we'll discuss it in a second. JSON LD, which we saw earlier. This is JSON linked data. Generic RDFA, microdata, Dublin core, microformats. So this list is not great for a specific reason, because this is mixing syntaxes and vocabularies. For me, okay, Open Graph and Twitter, okay, they kind of, one could argue that they're also syntaxes because they don't do things right, but they're Twitter and Facebook, so who cares? But they're actually more vocabularies. They provide a set of terms you can use rather than it should be like quote, open, blah, blah. These are the elements you use. So, but we'll talk about that in a second. So essentially, the key point is that all of these are RDF or RDF-ish. They're slightly broken RDF in some cases, but fine. Yeah. So Open Graph is essentially used by Facebook. I had to take a deep breath and go on Facebook yesterday to try to find some examples for this. It was kind of horrifying, but anyways. So this is not this post, by the way. I know this person. This is a post by Pascal, someone in my social network, who was posting a link to a webpage about some TED Talk. And essentially, Facebook knows what image to represent. It knows somehow a title of some information. It knows the description of what this page is about. And that's because if you go to that webpage for that TED Talk, and you look within the head of the HTML document, you'll find this metadata here, which uses OG, which refers to Open Graph, that states this is the URL of the webpage. This is the image you should use. This is a secure URL. This is the date it was released. These are some tags for what the page is about. So that helps Facebook. Then when you add a link, it knows what to represent or what to show in Facebook, in the Facebook post associated with that page. Yeah. So for this reason, it's highly popular to add this for search engine optimization or for generating traffic. Maybe search engine optimization is not the right term, but for generating traffic by having more attractive looking posts in social media about that page. Twitter cards is the exact same concept. So Twitter cards, if you post a link in Twitter, it can recognize rather than show an ugly URL, it can generate a nice looking link for you with an image, with the site, with the title, with the short description and so forth. And if we go to this page again, well, Twitter cards, I guess now it's X cards, but whatever. So if we go to this page, if we click on this link here in triathlon.org, and we go and we look into the HTML code, we'll find metadata again, and this is in a format that's almost RDFA. And it has some problems because Twitter just said, hey, we're going to invent our own syntax, and because we're Twitter, everybody has to use it. And people in the semantic web were like, what the hell are these people doing? We're going to have like 100 different formats for every big company, web company that exists, but fine. So it's almost RDFA. So we get some information here about what's the site, what's the title, what's the description, what's the image. It's almost redundant with Open Graph. So everybody has to find now the same data for a particular company and 1,000 different companies in the start or whatever. Okay. That didn't happen with the search engines. Thankfully, the search engines came to some agreement on what vocabularies to use. At least Google, Yahoo, Yandex, and Bing, I think, as well. Rather than having a Bing meta format and a Google meta format and a blah, blah, blah meta format, which would be a disaster, they kind of collaborated and said, no, we're not going to do that. We're going to use RDFA as a syntax and schema.org as a vocabulary. So if you search, for example, as mentioned, you get these rich snippets that gives you not just what's the title of the page, but also maybe some rating, how many votes it has. Sharknado, as we see here, not very much appreciated, kind of acquired taste by only civilized people enjoy this sort of movie. So if we look in the metadata, if we look in the HTML page, we find JSON LD. We find some chunk of JSON data in the head of the HTML document, which represents actually quite a rich description of information. This is only a small part of it. So one thing that's kind of boring when I say, okay, there's lots of RDF on the web, and it's basically Twitter cards that describes what's the title of the web page and a link, and in images is super boring, yeah. But actually, in the case of schema.org, that's not really the case. It's still missing some elements that would be cool, but you can get really rich data from this schema.org stuff. So in this case, we have some metadata for describing or being able to map this to RDF. We have the URL, the name, the image, the boring stuff, a description. But then we have information about aggregate ratings. There's some information here I skipped about a detailed review. We have aggregate ratings. This is the rating count. This is the best rating, worst rating, rating value, content rating not rated. We have genres. We have date published. We have information about the directors, the actors, the producers, the company, the duration. So we have actually quite a lot of of real data about the entity being described. And that's quite typical of schema.org because they actually like to represent this sort of metadata as part of the search results. Yeah, so if you wanted to, you could go check out those links. And if you go to a website, you can try to look to see what RDF is there. It's quite likely that you'll find RDF embedded in the web page. So that's the class. Any questions? Yeah.
I'm not sure. So what's the difference between like RDF and the JSON LD? Like,
yep.
Yeah.
So JSON LD was proposed as a sort of a format because JSON became so popular in terms of web applications and web development that people felt that it would be useful rather than trying to convince people not to use JSON, to try to look at ways to adapt or enhance JSON in order to be able to have the benefits of RDF as well. So it wasn't really thought of as a sort of, this is going to be another RDF syntax, but it's like, let's add web identifiers to JSON. Let's be able to say, to use vocabularies on the web, like schema.org within JSON, yeah, to be able to say, this is the relation, and you can click on this link and it gives you a description of what that thing is about. So people were looking for a minimal extension to JSON LD. So essentially that's what JSON LD is called. It's essentially an RDF syntax for JSON. It has a couple of elements that go beyond RDF. So it has things that RDF doesn't allow, but you can somehow automatically parse a JSON LD, documenting it back a graph of RDF data. I think I have an example here. Do I still have it open? Oh, sorry. Where is it? No, I closed it. No, it's here. So let me see. I can share this quickly for the people on Zoom as well. So this is the JSON LD. This is the full description of all the data that was in IMDb for Sharknado. So we see there's quite a bunch of data. So this is JSON LD format, and then we can, this is just a conversion of like a parser. We can submit that, and then it'll give us the RDF data that results from this. So we can extract JSON LD to RDF.
RDF is a syntax.
RDF, no, RDF I would say is a data model. It's a data model based on graphs and using these three different types of terms. And then we have for RDF, you have different syntaxes. One of them is turtle, n-triples, RDFA, JSON LD with a kind of slight asterisk. RDF XML. So not XML in general,
Yeah.
but like there's a special or XML syntax for RDF. Yeah. So RDF is a data model, and we can have different ways of describing that. But essentially, the data model is this thing here. Yeah, this graph of nodes with web identifiers, data types, and so forth. Right. Okay. More questions? If not, have a nice bank holiday tomorrow. Have a nice day, I guess. First of all, yeah. Monday's not over yet, but enjoy your bank holiday tomorrow. See you in Zoom as well.